So, what exactly is an integral transform? At its core, it's an operation that takes a function from one domain, like time or space, and maps it to a new function in a completely different domain. Mathematically, we write it as f of s equals the integral from a to b of f of t, times a special function called k of s and t, with respect to t. Here, f of t is our original function. K of s and t is known as the kernel. It's the heart of the transform and defines its type, like a key. The result, f of s, is the transformed function in the new domain. Think of it like translating a book. The original story in one language, say, the time domain, might be hard to analyze. By translating it into another language, the frequency domain, we can understand its themes and patterns much more easily. Why there is a dire need for integral transform? We transform functions to simplify and solve otherwise intractable problems. In the transformed domain, complex operations become simple. For instance, complicated differential equations often reduce to basic algebra. A messy mathematical operation called convolution becomes straightforward multiplication. More importantly, transformation gives us new insight, revealing hidden features like frequencies or growth rates. We solve or analyze the problem in this easier domain, and then use the inverse transform to bring the solution back to our original, physically meaningful world. Now, let's meet the superstar integral transform, the Fourier transform. Its kernel is the complex exponential, that is, e to the power of negative I omega t. It transforms a signal from the time or space domain into the frequency domain. It answers a fundamental question: what frequencies are present in the signal, and how strong are they? The mathematical form of Fourier transform is capital F of omega equals the integral from negative infinity to infinity of f of t times e to the negative I omega t dt. A perfect analogy is sound signal. In the time domain, a musical chord is just a wiggly line of pressure over time. The Fourier transform is like the musical score that breaks that chord down into the individual, pure notes or frequencies that make it up. Understanding the integral transform is only half of the story. When we solve a problem in the transformed domain, which in case of Fourier transform is frequency domain, we get a solution for f of omega, that is, the solution in the transformed domain, not f of t, which is solution in the original or real domain. To get our final, physical answer, we must bring it back. This requires the inverse Fourier transform. Think of it as a complete workflow, a two-way street. You take the problem to the frequency domain, solve it there, and then bring the solution back to the time domain. These two operations form a matched, inseparable pair. F of t is paired with capital F of omega. The forward transform uses the kernel e to the negative I omega t. The inverse transform uses its complex conjugate, e to the positive I omega t. They are mathematical opposites. One cannot exist without the other in the context of solving problems. Remember, the frequency domain answer is an intermediate, powerful simplification. The inverse transform is the crucial final step that translates your mathematical result back into the language of the real world. The representation of a complex signal in terms of its frequency and magnitude makes the Fourier transform ubiquitous. It's the foundation of digital signal processing, used in audio equalizers, image filters for blurring or sharpening, and compression of image and audio MP3 files. It's essential in communications for radio transmission, in engineering for vibration analysis, and in physics for solving equations like the heat equation. Next, we have the quintessential problem solver, the Laplace transform. Its kernel is e to the negative st, where s is a complex number combining growth and oscillation. It transforms from the time domain to the complex frequency, or S, domain. Its superpower is solving initial value problems for systems starting from rest. The equation is capital F of S equals the integral from 0 to infinity of f of t times e to the negative st dt. It excels at handling real-world complications like sudden shocks, switches, or discontinuous forces, and it automatically builds in the starting conditions. Solving a problem with the Laplace transform leaves us with a solution, capital F of S, in the abstract complex frequency domain referred as transformed domain. To complete the process, we absolutely need the inverse Laplace transform. Formally, the inverse is defined by a complex contour integral known as the Bromwich integral. But in practice, engineers and scientists almost never compute this directly. Instead, we use clever strategies. The most common is partial fraction decomposition. We algebraically break down a complicated capital F of S into a sum of simple terms that appear in standard lookup tables. For example, a term like 1 over S plus a in the table corresponds directly to the time function e2 minus at. This step is non-negotiable. The S-domain solution is just a convenient, intermediate representation. The inverse transform is what delivers the tangible result, the actual voltage over time, the displacement of a spring, or the concentration of a chemical in a reactor. Remember, the Laplace transform and its inverse are a locked pair. The notation symbolizes this complete, two-way relationship. You cannot have a final answer without applying the inverse. You will find the Laplace transform at work in electrical engineering, analyzing how circuits respond when you flip a switch. It is also critical in control systems for designing stable autopilots for aircraft or process controllers in chemical plants, and in mechanical engineering for modeling vibrations and damping. Now compare the key integral transforms side by side, looking at their kernels and primary roles. The Fourier transform uses the complex exponential kernel, moving from time to frequency. Its core importance is spectral analysis, uncovering the frequency makeup of a signal. The Laplace transform uses a decaying exponential kernel, moving to the complex frequency domain. It is the fundamental tool for system dynamics, solving initial value problems in engineering. The wavelet transform uses a flexible, localized wavelet kernel. Its strength is multi-resolution analysis, perfect for signals where features change over time. The Z transform is the discrete time equivalent of the Laplace transform, using Z to the power n. It's indispensable for analyzing digital systems and filters. The Hilbert transform uses a Cauchy principal value kernel. It's specialized for creating an analytic signal to examine envelopes and instantaneous phase. The Hankel transform uses a Bessel function kernel and is tailored for problems with cylindrical symmetry, like analyzing vibrations in a circular membrane. The Mellin transform uses a power law kernel and is used for analyzing scaling properties in functions and number theory. Finally, the Radon transform is the mathematical backbone of tomography, reconstructing images from projections, as in medical CT scans. Each transform is a specialized lens, chosen based on the symmetry of the problem and the type of information you need to extract. Despite their differences among various integral transforms, all integral transforms follow a common ecosystem. First, you choose the right tool, the right kernel, for your problem. Second, you transform the problem into an easier domain. Third, you solve or manipulate it there, often with simple algebra. Finally, you use the inverse transform to bring the solution home. This workflow is a universal problem-solving strategy.